Hello guys, hope you're doing well. And as always, if you're new to my channel, I would request you to subscribe to my channel. Thank you. Okay, so the problem at our hand today is that we need to replace the distributed loading by an equivalent resultant force and specify its location measured from point A. Okay, so the distributed loading is basically from A starting as 800 Newton per meter and it is going up till this point. Okay, this is the distributed loading 800 Newton per meter. Okay, and the other loading at point B is given as 200 Newton per meter, and the distance from A to this point where this square ends is 2 meters, and from this point to point B it is 3 meters. Okay, so this is about the geometry of the figure. Okay, so we can easily see in this picture that this square can be treated as approximated as figure 1. Okay, which is basically a square one, and if we draw a straight line from this point to this point, basically from this point to this point we can see a triangle is being formed. We call this as triangle 2, and from this point to this point, if you go down, we can see a rectangle is being formulated, and we call this as rectangle 3. Okay, now we calculate the dimension, the loading aspects of our figure 1. Okay, which is basically a square. So the equivalent force for square 1 will be Fr1 equals to, it is nothing but the area of the square, which is nothing but the breadth and the height. Okay, and how we calculate this resultant force for figure 1, which is basically again a square, is 800 Newton per meter multiplied by 2 meter. So we get Fr1 equals to 1600 Newton. Okay, so just to see, if you look at it, this resultant force Fr1 is nothing but the area of the square, which is the height 800 Newton per meter, and the base, which is the 2 meter, and that area comes out to be as the resultant force 1600 Newton. Now if we go to rectangle 3, which is this one, we can very easily see that the height of this rectangle is basically 200 Newton per meter, and the base of this rectangle is 3 meters. So if we multiply both of them, we get the resultant force Fr3 equals to 600 Newton. Now we go to this triangle, which is starting from this point to this point, and in order to calculate the resultant force of this triangle, we call it as Fr2, and is basically going to be the area of this triangle, which is nothing but half into base into height. But what is the base of this triangle from this point to this is 3 meters, and what will be the height from here to this red line ends? We can very easily calculate it as 800 Newton per meter minus 200 Newton, so it will be giving as 600 Newton per meter. So here we have done the calculation, and we get the resultant force of this triangle is basically 900 Newton. Okay, so we get it as 900 Newton. How we get it? Because 800 minus 200 is 600 Newton per meter multiplied by 300 is how much? 1800, and divided by 2 will give us basically 900 Newton. So this is how we have calculated Fr2, we have calculated Fr3, and we have also calculated Fr1. Okay, now once this is being done, now we need to calculate the resultant force of the system. So resultant force is nothing but the sum of the individual resultant forces of these rectangle, square and triangle, which is 1600, 900 and 600. It gives us as 3100 Newton. Now to specify the location of this centroid of Fr from A, as he has said, you need to specify the location measured from point A. We can write this equation that summation of the moments of the resultant force, which is moment of Fr, equals to summation of the moments at A and the moments of the individual forces, which is F1, F2 and F3. Okay, and taking use of this equation, we go to the next page, and here we say that the resultant force will be Fr, the moment of the resultant force will be Fr into x bar, which is being shown over here, and it will be always equal to the individual moments created by the square, rectangle and triangle. So it will be 1600. The moment of this square will be 1600, and half of this 2 is basically 1, plus if you look at it over here, for the other component, that is for the this triangle we have over here, it will be nothing but it will be the area of the triangle. It will be nothing but the area of the triangle, which we have basically calculated as the centroid, which is located at C, for this area of this triangle, which is this C. So how we calculate this 3 is very important, because we know that the centroid of the triangle is located at this point C, and we assume the length of this triangle is x. If this is the scenario, we can say the centroid will always be located at 1/3 of this length, which is starts from here to this point, and the other area, which is other, will be 2 x of by 3. It is 1/3 of the length and 2/3 of this length. So if this is x, from here to here it will be x by 3, and from here to here it will be 2x by 3. So the same logic we have done for this triangle. So from A, if you calculate the length, it will be basically from the triangle, which is basically this one, it will be 2 meters from here to here, plus basically x by 3 of this total length, which means the x is 3, and divided by 3 it will give me 1, since x equals to 3. So it will be 2 plus 1. This remember, this x is this one. Okay, so 2 plus 1 is equals to 3. So that is why we get 900 into 3. And what about this rectangle, whose basically resultant force is 600, multiply by we take the centroid of this rectangle is basically center of 3 meters. The exact half of this 3 meters will be 3 by 2, and which is going to be at somewhere in the middle, making it as 1.5, and from A the distance will be 1.5 plus 2. So we'll be writing as 2 plus 3 by 2 as the moment arm. So when we calculate it, we get our resultant centroidal location of Fr will be equals to 2.06 meters. Okay, so this is how we have solved this problem. I hope this solution will help you. You have a wonderful day. Thanks and take care.